Right. So, in our course selected topics in decision modeling, we are in our 37th lecture, that is on taboo search. Now, taboo search is a meta heuristic technique which guides a local heuristic search procedure, and it explores the solution space beyond local optimum by using a taboo list. So, what is a taboo list? The taboo list is a set of solutions which are not to be used anymore, in a sense forbidden. And it uses the flexible memory structure in conjunction with strategic restrictions and aspiration levels. What is aspiration level, we shall come a little later, and kind of problem that it solves are all combinatorial in nature and obviously with a finite solution space. And it is a neighborhood search method. So, that means once we have a point, it searches around its neighbors, and there is a flexible memory structure. So, there are three broad strategies in taboo search. There is the forbidding strategy, that what goes into the taboo list, and freeing strategy, under which condition that we take out from the taboo list. And then there is also short term strategy that manages the interplay between the forbidding and freeing strategies for select trial solutions. Now, the question is that what goes into the taboo list and what comes out of the taboo list. So, let us have an example. Supposing we have a problem, let us say the problem on traveling salesman problem, TS problem, where a person goes from one city to all the other cities and comes back to the same city. Supposing there is a 5 city problem, there are 5 cities and the person has to go to one city to another city and then come back to the same city. So, assume that 21543 is the current solution. That means 2 to 1, to 1 to 5, to 5 to 4, to 4 to 3 and 3 to 2. So, that is say our code. Now, what happens? Let us say that supposing we are minimizing the distance, and the current distance is d equal to 50. Now, assume I interchange 1 and 4, the location 1 and 4, and then we get a new solution 24513. So, 24513 is a solution which is a neighboring solution, I may call it a neighboring solution. So, this neighboring solution that we have got, and let us say it improves the solution value from 50 to 55. So, what has happened? By interchanging one and 4, we got an improvement from 50 to 55. Is it all right? The question is that should I again allow these 1 and 4 to be interchanged? Look here, at this solution 1 and 4 are interchanged and we have got something better, but if we interchange again, then it will become worse, is it not? So, what we do, we then put a restriction that 4 to 1 goes to taboo list. 4 to 1 goes to taboo list. Why 4 to 1 goes to taboo list? And let us say for certain period, say for example, say for 3 periods. So, for the coming 3 periods, we shall not be doing 4 to 1 switch, because by 1 to 4 switch we have come here. If we do again, then we go back to the old solution with a loss of objective function value. So, we should not do that. Is it all right? So, this is what is actually the taboo list, and but at a later stage it may so happen that we have maybe another current solution which may be very different. Say for example, it could be 3 and then 4 and then 2 and then 1 and then 5. Look here, this 3, 4, 2, 1, 5 is a very different kind of solution. So, now this 4, 1 which was originally in the taboo, that is that 4 to 1 interchange, which may not be meaningful anymore. So, by these interchange we may get actually even better solution. So, these are the things that we need to think about. So, that would be our aspiration level. Is it all right? So, to really get something better by removing the taboo. Is all right. So, this is precisely what these different strategies actually mean, right. So, having known this, let us look some of the basic ingredients of the taboo search method. So, first of all, it is a primary way to exploit memory in taboo search by classifying a subset of the moves in a neighborhood as forbidden or taboo. And a neighborhood is constructed to identify adjacent solutions that can be reached from the current solution. The classification based on the search history and the frequency that certain move or solution component called attributes are participated in generating past solutions. And then taboo list records forbidden moves which are referred to as taboo moves. Then this is exactly what I was telling, that about that freeing strategy. The aspiration criteria provide exception to taboo restrictions. When a taboo move has a sufficiently attractive evaluation where it would result in a solution better than any visited so far, then its taboo classification may be overridden, right. The example I was giving about the travelling salesman problem, one move that was under taboo list earlier is really going to give better solutions in the next set of iterations, and in that kind of situation we have what is known as the aspiration criteria. Fine. So, having known this, let us move over and look at the basic taboo search algorithm. The first, choose an initial solution I in the solution space and then set I star equal to 0 and a parameter number of iterations k equal to 0. Now, set k equal to k1 and generate a subset V star of the solutions in NIK. NIK is the neighboring solution of that initial solution I. Is it all right? And such that either one of the taboo conditions is violated or at least one of the aspiration conditions holds. So, after that choose a best j in V star and set I equal to j. What does it mean? So, in the neighborhood we have say found out some solutions which are better than the current one. Is it all right? So, better, or they are evaluated with the best of their what is called functional value, and they are listed as sorted. Now, at least suppose one such solution in the neighborhood is found for which this condition is satisfied. What is that condition? That is f I star is better than f I. Obviously, in a maximization problem the value will be higher, the new value is higher. In a minimization problem the new value is lower. So, that means that we have a certain value, objective function value, the new value is better than the previous value. Then what happens? That becomes our current solution. So, that is set I star equal to I. So, now we should really look from that point of view. Now, update taboo and aspiration conditions. Aspiration conditions could be that increases objective function value by a certain amount, and if a stopping condition is met, then stop, else continue. Is all right. So, this is how the basic taboo search algorithm works. Fine. So, having known that, let us see some stopping criteria. The stopping criteria is that there is no feasible solution in the neighborhood of the solution I, right. That means, we cannot find a neighborhood. Then k is larger than the maximum number of iterations allowed. That means, total number of iterations are exhausted. And then number of iterations since the last improvement of I star is larger than the specified number. That means, we are iterating for quite some time, but we are not really getting any further improvement. That means, convergence is reached, and there is evidence that an optimum solution has been obtained. Suppose we have otherwise some method to know what is the vicinity of the optimum solution. Suppose we have some kind of the what you call as this control limits, something like the bounds, like upper bounds or lower bounds, and we have estimated those bounds, and the bound solution is reached, then obviously there is no point continuing any more. So, this is how it in a flow chart kind of thing, that we have an initial solution. So, from the initial solution create a condition candidate list of solutions in the neighborhood, then evaluate the solutions, choose the best one, then stopping condition satisfied, then final solution, otherwise update taboo and aspiration conditions and continue, right. So, that is the taboo search algorithm flow list. So, having seen that, next we continue and see what are some advantages and disadvantages before taking up a practical problem. So, advantages: accepts non-improving solution so as to escape from a local optimum, can be applied to both discrete and continuous solution spaces, can be used for complex problems like scheduling, quadratic assignment, vehicle routing, and also obtains competitive solutions vis-a-vis other similar approaches. Disadvantages: too many parameters, large number of iterations, and like any meta heuristic method, global optimum is not guaranteed. Is all right. We may or may not get the global optimum solution. So, that is some of the disadvantages of the taboo search method, right. Now, let us look at a particular problem. Suppose we have 6 jobs that is to be done in a sequence that an objective function is maximized. The objective function may be profit from the reduced tardiness. The tardiness is basically lateness. So, usually what happens that in a shop condition there are several jobs to be done, and maybe they all require certain crew or certain people or certain machines, certain facilities, so that at a time only one job can be done. Now, each job has a due date, is it not, and each job requires certain number of days to be performed. So, depending on, suppose job number 5 you do first, and then 3, then 4, then 6, then 1, then 2, you get one set of lateness of jobs. Maybe 5 is not late, but 3 is late, 4 is late also, 1 is not late because one's due date was pretty far ahead, and 2 is also not late. So, what happens? What is the total lateness of all these jobs? And is it not? So, like these we can compute the tardiness, and if you can reduce the tardiness, obviously the profit is going to go up. So, assume that we are maximizing some objective function. What is that objective function? We are not going into the detail. So, this is one solution, is it not? 5 3 4 6 1 2. So, what could be a neighbor? A neighbor could be by swapping these jobs, we can get the neighborhood structure. So, how many such neighborhood structures are possible? See, there are 6 jobs. So, we can have 15 possible swapping of these 6 jobs, is it not? Because these 5 could be going to any of these 5 positions. So, similarly, all these 6 can go into any of these, I mean 3 can go to rest of the 5 positions, 2 can go to rest of the 5 positions. So, 6 into 5, 30 possible combinations, but then each combination has a double. What does it mean? It means say 5 to 3 and 3 to 5. So, basically 5 3 swap and 3 5 swap essentially same, because after all 5 is here and 3 is here. So, that is how that 5 into 6 by 2 equal to 15 possible swaps, right. So, 15 possible job swaps are possible. So, that is how we have the solution has got 15 neighbors. I hope it is understood that 15 possible way the jobs can be swapped. So, that means the neighborhood structure has 15 possible solutions, is it all right. So, the question is that we should evaluate them and we should see which one is giving us a better possible solution, right. So, let us see further. Then we have, let us say, these recency based memory and taboo classification for this problem. Then how do we go about it? So, 3 most recent job swaps are classified as taboo for the problem considered. Thus, the taboo tenure will be for 3 iterations, and aspiration criteria is made use of to take some job swaps out of taboo. So, let us see that 5 3 4 6 1 2 with a 4 2 swap, we have 2 4 as taboo for 3 iterations, right. So, look here, this is where we have put taboo structure, because you see once 4 and 2 are swapped, then we have 2 to 4. Obviously, we can mention it at 2 to 4, there is only one square between 2 and 4 in this taboo structure. So, that means since 2 to 4 is already here, automatically it means that taboo is the reverse direction, that is 4 to 2. So, we just need these this kind of triangular structure should be sufficient to hold all the taboo structures. So, that is the thing. So, now 2 4 is taboo and taboo for 3 iterations. So, this is our taboo list. So, right. So, if this is our starting solution and this is our new solution with a 4 to 2 swap, then 2 to 4 should be taboo for 3 next iterations. So, this is how the recency based memory and taboo classification can be carried out. Now, let us see what happens in the 0th iteration. So, let us say our original current solution is 5 3 4 6 1 2 and objective function value is 20. Question is how do we get it? So, I have not shown details. So, I just assume that this much is available for the given objective function. So, and now there is nothing in the taboo structure. So, that is how where the problem we have started about 6 jobs, and let us say the top 4 candidates in the nearby are a 5 4 what you call swap, a 3 6 swap, a 3 2 swap and a 4 1 swap. Now, what are the result? The result is if you do a 5 4 swap, your objective function value improves by 5, second one improves by 3, third one improves by 1, but the fourth one it objective function value goes from 20 to 16. That means, it is not an improvement, it is a decrease. So, out of all these, the best possible solution is found for a 5 to 4 swap. So, you can see that this one is the best possible swap that we can have. So, obviously, we choose it, that means we choose a 5 to 4 swap after the iteration 0. Now, as we do that, what is resulted? Let us see that. So, at the next iteration, this is what we have. So, please see our previous iteration, we have 5, 3, 4, 6, 1, 2, and in the next iteration 5 and 4 are swapped. So, we have 4, 3, 5, 6, 1, 2, and objective function value becomes 25. Why 25? Because it improves by 5. So, 5, 3, 4, 6, 1, 2 becomes 4, 3, 5, 6, 1, 2 with an objective function value of 25, and 4, 5 will be in taboo for 3 iterations. So, you see, because 5 to 4 swap we had done, now 4 to 5 swap we should not do for 3 iterations. So, it is in the taboo list, is all right. Now, again we have to evaluate in the neighborhood what are the top candidates. So, we have decided to see top 4 candidates. So, these are our top 4 candidates. So, we see that 3 1 gives us an increase of 3. So, that is the best possible solution that we can get at this point, right. So, in the previously we have 5 and 4 we have swapped, and now as 3 to 1 swap is going to give us further improvement by 3, is all right. So, should we go for it? Yes, we should go for that. So, we have gone for that, and then look here, we have made 3 and 1 swap, and now we have 1 and 3. So, our new job sequence is 4 1 5 6 3 2, and objective function value has improved from 25 to 28, is it all right. So, it has gone from 25 to 28. Now, the taboo structure. So, you see in the earlier one the 4 5 was only under taboo, and since 3 to 1 swap we have done previously. So, 1 to 3 should actually be taboo also, is it all right. So, 1 to 3 should be in the taboo now. So, 1 to 3 will be taboo for 3 iterations, and 4 to 5 already 1 iteration gone. So, this is also in the taboo for 2 more iterations, and objective function value is 28. So, again we evaluate top 4 candidates, and then what do we find? 1 3, 4 2, 4 5, 6 2. But look here, none of them improves the objective function value, none of them. So, actually they are -3, -4, -6 and -7, and -4 is the best. The question is, should we do it or should not we do it? So, it depends on the particular aspiration level or particular way we conduct the taboo. In this particular one we decide to go for it, because sometimes even though the objective function value is reduced, maybe in future it might give us some better points. Suppose that search yields nothing, then we can come back here and we can say, look here, that is the best that we have got so far, is all right. So, with that thinking we decide to explore 4 to 2 further. Why 4 to 2? Why not 1 by 3? Because 1 to 3 swap is a taboo, that is in the taboo list. So, that cannot be considered. So, understood that 1 to 3 cannot be considered because it is taboo. The 4 to 5 cannot be considered because it is in taboo, and 4 to 2 is then best possible thing, although that best is also not that good because it reduces the objective function by 4. We decide to still go for it, right, so that we may explore around or in the neighborhood of that point, and who knows, we might get something better in the next iteration. So, that is what we do, and after that swap, that means 4 to 2 swap, now we got 2 to 4, 2 1 5 6 3 4, and objective function value you see has come down from 28 to 24. So, as we have that, what we get then the taboo structure, see look here, earlier our taboo structure was 1 3 and 4 2. that was 3 and 2 iterations. So, it has now come down by 1 more. So, 1 3 by 2 more iterations and 4 to 5 as just 1 more iteration. And what are my top 4 candidates now? Look here, now 1 3 has come out as best, followed by 2 5, 1 4 and 6 4. So, 1 3 that it is in taboo, but it is best, and it is going to give us improvement of objective function by 5. So, actually it satisfies our aspiration criteria. How it satisfies? Let us look at that. So, look here, so far our best solution is 28, right, and current solution is 24. 1 by 3 swap is giving us 5 extra. Now, question is that same 1 3 which was negative earlier, how come it has become positive now? It is very clear, because now the string has changed and we are now searching in a different neighborhood. So, how much we are going to get? 24 plus 5, that is equal to 29, and 29 is better than 28, right. So, 29 is better than 28. Since 29 is better than 28, it really satisfies our aspiration criteria. That means, the aspiration criteria could be the resulting solution is better than the best obtained so far, right. So, that is sufficient really to take 1 3 out of the taboo. So, if I take 1 3 out of the taboo, it gives sufficient thing to take 1 3 out of the taboo. So, we decide to do that. That means, although 1 3 was taboo, but now we decide to take it out from the taboo list. That means, that is a freeing strategy, right. So, this is exactly what is that through the aspiration criteria we take something out of the taboo list. So, we do that and we get our 4th iteration, that is, see, look here, 1 3 is now become 3 1. So, 2 3 5 6 1 4, and the objective function value has improved by 5, it has become 29. So, since our new list would be then, see, last movement was our 1 3. So, now 3 1 should be taboo, right, and so this is the new top 4 candidates. 5 1 is 0, that is best, 3 6 minus 1, 1 4 minus 2 and 3 1 minus 5. So, this will be now taboo, that is 3 2 1, and because the order is 3 to 1. So, automatic it should be the other way, should be movement, is it not. So, here, so this is that 3 1 is that. So, this taboo should be then again 1 3, right, not 3 1, it should be then 1 3, right. So, that is how it is, that is that we have our new list. So, 5 1 does not improve objective function, hence after 4 iterations the current solution objective function value comes out to be 29. So, this is how we really solve the taboo search problem. So, before leaving, let us very quickly go through another problem, although we do not solve it, but just try to give a general idea of that problem very quickly. So, this problem is something like this, that a retailer allocation. So, supposing there are some distributors and there are some retailers. So, there are 5 distributors and 5 retailers. Now, each distributor has to be allotted a retailer. So, look here, there are 120 such alternatives. Even such a small problem of allocating 5 distributors to 5 retailers has got 120 different alternatives, is all right. And there is a distance matrix and there is a cost matrix, right. So, there are distances between those distributors and retailers, and there is also certain cost that is considered between them. So, supposing some options, suppose 1 is allotted to 2, 2 is allotted to 3, 3 is allotted to 1, 4 is to 4 and 5 is to 5, the cost is 2354. Similarly, different other combinations are shown here with different cost of assignments, is all right. So, these are maybe some typical solutions, right. So, how we can encode that? We can encode that distributors 1, 2, 3, 4, 5 and retailers may be 1, 5, 2, 4, 3. That means 1 to 1, 2 to 5, 3 to 2, 4 to 4, 5 to 3. Actually, that first row is not even required, second row is sufficient, automatically means this is going to this. So, suppose the fitness is 1 by total cost of transportation, and total cost of transportation is the distance multiplied by unit cost. So, therefore, the fitness for this particular configuration could be say 0.00139, and our job is to minimize total cost of transportation or maximize fitness, is all right. So, that is how it is, and that is when you try to solve this by taboo search, inherent simplicity and all that initial solution is randomly generated, algorithm finds the best admissible next solution at each thing, and taboo list is obtained. So, some of this is how already I have shown how it should be done, and say from one such coding we can do either one step forward move or one step backward move. And by the kind of problem that we have shown earlier, in the similar way we can solve this problem. So, how it is one step forward? 5 has moved here, and 5, that means as 5 has come forward, this 2 has actually come and 5 has gone back, and here one step backward, that means the rest of that 1 has. So, 5 as if 5 has gone ahead of 1 and 1 has gone, that is how that is called the backward move. And when solved, the comparative result shows against simulated annealing, same solution is found, although taboo search took more generations or iterations, and average time best solutions obtained in 100 runs, taboo search is slightly better, is all right. So, that is how it is. So, these are some of the remarks about taboo search, and I hope you got some basic idea of the taboo search technique, although it is not sufficient to solve realistic problems, but our purpose is to give a general idea. So, thank you very much.